Hello, this is Matt Nelson, and in today's video I'd like to take a look at logistic regression. So we have a data set here of pizza deliveries, and we have the delivery time in minutes and the temperature of the pizza delivered in Celsius, and we have a yes or no column for whether or not the customer left a bad review. So unlike linear regression, where the output is a quantity, and the variables are a straight line relationship, here we have a probability distribution that is binomial. That is, it is binary 0 or 1. So how do we answer the question, what is the probability that a customer will leave a bad review based on the delivery time and temperature? So to perform that analysis, we need to make a model using logistic regression. It's logistic because it follows the logistic function, which is a sigmoid distribution of probabilities, or an S-curve. So to get started, we need to write some coefficients for our model. So first we need, as always, an intercept. We need the time coefficient and the temperature coefficient. So in this column, I'm just going to name the cell intercept, this one time coefficient, and this one temperature coefficient. Now that I have these cell values, I'll put some borders on them. I'm going to initialize the model with an intercept of 1 and 0 for time and temperature. We're going to use Excel's solver capabilities to figure out what these coefficients are. So what is the output for our model? The output is a value called the logit, which is the natural log of the odds. We can't output the probability directly because we'll end up with problems dealing with negative numbers and exceeding 0 or 1 for probability. So instead we take the logit function, and this will give us the log of the odds, which is our output. So our output is the intercept plus the time coefficient times B6 plus the temperature coefficient times C6. So to start out, the logit is going to be 1. Now we have to do some workarounds to extract the probability. So the first thing we need to do is take the anti-log in order to get the odds. So we use the exp function times d6, and this gives us Euler's number, E. But this is the output in odds. We want to have the probability of a bad review. So that would be the probability would be the odds over 1 plus the odds, 0.73. So this is the output of our model, but we want to get the probability of actual outcome. Which is going to rely on a conditional function. So if the bad review in A6 is 1, then we want to use the probability of a bad review in F6, otherwise we want 1 minus F6. So the columns with 1 here is the probability of a bad review. So now we're not done yet. We need to take now the log of the likelihood, which is simply the natural log of G6. Now we can talk to our model in a format that it understands. So what's the goal of optimizing this function? We want to maximize the sum of all these log likelihoods. So sum of LL equals the sum of H6 through H979. And we have a pretty low number here, and hopefully if our coefficients are statistically significant, we can increase this number and get as close to 0 as possible. If it's 0, that means we can predict absolutely accurately whether or not a bad review will be left. So let's use the solver function on the data tab. And we want to maximize H3 by changing the intercept, time, and temperature coefficients. And we want to make sure that we uncheck unconstrained variables as the non-negative, and then go to options. And for our non-linear algorithm, we want to make sure we're using central convergence and uncheck require bounds on variables. We can put in more decimal places if we'd like. And OK, and then solve. And solver has found a solution. Okay, so now we have a model that predicts the probability of leaving a bad review. Is our model statistically significant or not? Well, we can look at the full model, and the sum of log likelihood that we got was negative 224, which is a very big improvement over 100. And now let's look at the model restricted to just the intercept. So let's look at our coefficients. So to do that, let's run solver again. This time subject to the constraints where the coefficients are equal to 0. And solve. Solver also found a solution, and this time it's 408. Now, to test statistical significance, we can't check this directly. It turns out that we need to take, first of all, the difference or the deviance between the restricted model and the full model, and then multiply by -2, or this gives us the value g as it's known. So we'll do -2 times the difference, and that gives us a g value of 366, which is a very high number for a chi-squared right tail distribution, and we'll test that using the function chi-squared distribution right-tailed. And we'll take the g value for x, and we'll use 2 degrees of freedom representing our two variables. And we have a test very, very close to 0, showing that this is indeed statistically significant. So this is useful anytime you want to answer a yes or no question and create predictive analysis based on a binary outcome. So I hope you enjoyed this video. If you do, please remember to like, comment, and subscribe. Thanks for watching.